photofenton process and electrofenton process. And my dear friends, my area is Fenton process. Now, advanced oxidation process, if I tell you, it is used for degrading the organic compound with the help of an oxidant. And it is not necessary that a given compound will be oxidized completely. It is not necessary. The concentration may come down a little bit, and that we call it as partial oxidation, and that partial oxidation is sufficient for that particular so that effluent can be subjected to biological treatment. And AOPs, they normally, I told you, they involve the generation and use of free hydroxyl radical, which is a very, very strong oxidant, very, very strong oxidant when we compare it with ozone, oxygen, or chlorine. So this is the best oxidant, and it is readily available oxidant, and this reacts with dissolved constituents, and then it converts the organic compound that is present in the wastewater as a contaminant into CO2 and H2O. So advanced oxidation process, here you can see the influent organics, okay, that organics that are present in the wastewater are subjected to oxidation, and we get less toxic CO2, and we get more biodegradable contaminants that are still present in the wastewater. Now, Fenton process, what is Fenton process? Fenton process deals with presence of hydrogen peroxide and ferrous iron. Here, hydrogen peroxide is the source of OH radical, which is generated in the presence of ferrous iron. This ferrous iron is playing the role of a catalyst. Okay, so if you see here in the chemical reaction, I have written here that this Fe2 plus reacts with H2O2, and it helps in the generation of OH radical, and itself it gets converted into Fe3 plus ion. Now this Fe3 plus, here it said the reaction does not stop. There is continuous generation of OH radical. How come? Because Fe3 plus then again reacts with H2O2 that is still present in the water, that is still present in the mixture, and it again gets converted into Fe2 plus. So this cycle of generation of OH radical is continuous. And then, but there is a certain concentration up to which H2O2 can be added. After a certain concentration of H2O2, that particular concentration of H2O2 is known as critical concentration. After a certain critical concentration of H2O2, certain side reactions starts taking place. And those side reactions, during those side reaction, OH radical is removed. And if the OH radical that is present in the mixture gets removed, then further oxidation reaction stops. So first thing that we need to find out is the critical concentration of H2O2, wherein the OH radical generation is continuous and side reactions does not take place. You can see in this particular chemical reaction that how H2O2 itself is scavenging the OH radical. So this, now I'm going to share with you some of my case studies that I have done. The first one is I have treated synthetic dye bath waste using pickling waste as an inexpensive iron source. Now I think I've made it clear that in Fenton process I need H2O2 and I need an iron source, and that iron source in Fenton process is ferrous sulfate. Now, instead of ferrous sulfate, here I have used pickling waste. Now, before I go into the detail of pickling waste, I would like to tell you why I have chosen the dye bath wastewater, because dyes are normally used in textile industry, and textile industry is one of the major polluting industries. You can see here that around 17 to 20% of industrial wastewater solution comes for textile dyeing. So that is why I have chose, and this wastewater has a strong impact. I told you, if they discharge it directly into the source of water, these dyes are strong chemicals. They are strong organic compounds. So they will utilize the DO that is present in the wastewater, and they have a very, very complex chemical structure, and these dyes are normally non-biodegradable. Normally they are non-biodegradable, and they are resistant to destruction by conventional wastewater treatments. So that is why this I have chosen textile wastewater for the treating it using Fenton process. So now in this, I told you I have used pickling waste. Now, what is pickling waste? Pickling waste is again a waste that is obtained from a steel industry. Okay, that is wherein in steel industry they use some acid. It can be either H2SO4 or HCl for removing the rust that is present on the iron sulfur, on the iron surface. Okay, so that pickling waste contains lot of iron in the form of ferrous, that is Fe2 plus. So I have used ferrous, this pickling waste as a source of Fe2 plus. So if I tell you, I have used a waste for treating a waste. I have not used ferrous sulfate, but I have used a waste obtained from one industry, that is steel industry, for treating a waste of another industry, that is your textile industry. And in this, the pickling liquor was characterized to see what is the concentration of iron that is present there. It contained 80 gram, and the pH was more than 2. And dye bath I have prepared, I have used those dyes which are difficult to degrade and that are normally used in textile industry in dyeing units. That is RB4, reactive blue 4, RO16, that is reactive orange 16, and the initial COD of this particular COD's chemical oxygen demand was 420 ppm, and the pH was 10.5. Now, this is how the dye bath wastewater was prepared by me, by our group. And then in the experiment, we performed the Fenton oxidation, wherein we optimized the time, doses of iron, and doses of H2O2. So the time was optimized, wherein we conducted the reactions. This is iron dose optimization. Time optimization was done, wherein we conducted these reactions for 4 different period of duration. That was 30 minutes, 60 minutes, 30 minutes, and 120 minutes. Now, before, let me tell you one thing, that for Fenton process, a pH of almost 3.5 to 4 is required, because at higher pH, Fe2 plus gets precipitated out in the presence of as Fe3 plus, that is iron hydroxide. So we want that in the because this reaction is carried out in the presence of Fe2 plus, and the role of Fe2 plus is very, very important. That is why here the role of pH is very, very important. That is 3.5 to 4. So initially a pH of 3.5 to 4 is maintained, and then at 100 ppm of iron dose, the fixed dose of iron is done, and a fixed dose of H2O2 is maintained of 26.4 millimolar, and the time is varied from 30 minutes to 120 minutes. And once after the duration, set duration of time, the pH was adjusted to more than 7 to remove iron now in the form of iron hydroxide. And then the solution that we got, the supernatant solution that we got, it was subjected to study the variation in COD levels, and also to study the decrease in the level or concentrations of RB4 and RO16. And on the same basis, iron dose optimization was done and H2O2 dose optimization was done. And in iron dose optimization, now the maximum removal, color removal or COD reduction that we obtained when time was optimized, that time was kept constant here for doing iron dose optimization and H2O2 dose optimization. Then when the doses were optimized, analysis of samples were done in terms of seeing the measuring concentration of RB4 and RO16, and this was done using spectrophotometer, wherein the lambda max of RB4 of 599 and lambda max of RO60 of 493 was measured. And similarly, COD was done using this batch reactor. And then this is the result. If you see that maximum color removal and maximum reduction in COD was obtained after a period of 2 hours. Now this I can show you in the form of table. If you see in the table that the time was varied from 30 to 120 minutes, you can see that after a period of 120 minutes, that is 2 hours, maximum removal of concentration of the initial concentration of RB4 was 100, it came down to 23.2. That means 21.65% removal percentage removal was there. Due to RO16, the concentration of RO16 was 25 and it came down to 0.79. That means 16% was removed, and COD was removed 40%. Wherein in all the other cases, when the reaction was carried out at 30 minutes, so the COD reduction was only 12.4. Now, if you concentrate here, as the time was increasing, the percentage removal was also increasing. Here also you can see in all the cases, the percentage removal was increasing as the percentage of time, as duration of time was increased. So maximum this removal took place at 2 hours. Now, similarly, you can see it through this graph also that we have plotted this time versus minus log C. You can see that we have calculated the slope, that is rate of reaction also we have calculated. All the studies were done on this, and this is that is for decolorization, and this is for reduction in COD. Now, similarly, iron dose were optimized. Now, the iron dose was varied from 100 to 500 milligram per liter. And here also you can see the maximum reduction that we got was at 500 ppm. At 100 ppm, only this much removal was done. Whereas when iron dose was increased to 500 ppm, here you can see the time was kept constant at 2 hours, and the H2O2 dose was 26.4 millimolar. So we got maximum removal at 500 milligram per liter of iron dose. Now similar, these are the graphs that were plotted to show how the iron dose increasing the iron dose helped in the removal of color as well as helped in the removal of or reduction in COD values. H2O2 dose was varied. Now there you can see that the maximum time was 2 hours. Optimized time required was 2 hours. Maximum iron dose was 500 milligram per liter. Now keeping these two constant, the doses of H2O2 were varied. And here now if you see, here like I told you, H2O2 dose plays a very, very important role because at higher concentrations of H2O2, the scavenging reaction starts. So if you see here, what is the that is critical concentration of H2O2. If you see here, from 26.4 to 61.8, there was increase, and then after 61.8, the concentration or this started decreasing. So the critical concentration of H2O2 was fixed at 61.8 millimolar, that is 7 ml. And my dear friends, let me tell you, after optimizing H2O2, again to confirm whether this H2O2 dose is okay or not, and this H2O2 dose, is it okay with all 100, 200, 300 ppm? The reactions were repeated, and 500 ppm of iron dose was optimized, 2 hours was optimized, and all these optimized doses. And here you can see here, initially when there is increase in the concentration of H2O2, increase in the concentration of H2O2, you can see there is reduction in the COD values. And after this, there is what is happening, that there is the rate of reduction in COD values is good, but after this we are not seeing any changes. So that means H2O2, this is the optimum dose or the critical concentration of H2O2. Now, some people may say that when ferrous sulfate is the best one, and you are saying that you have used pickling liquor, then how do you say that pickling liquor can be used instead of FeSO4? So then we performed the study with FeSO4. All the studies were done using FeSO4, and you can see here that when FeSO4 was used, you can see here we were getting this almost comparable results. Time 120, RB4 90% removal, FeSO4 90% removal, RO60 96% removal, 96.4% removal, COD 62% reduction, and here 52%. So you can see that pickling waste can be used instead of FeSO4, and the advantage of this is we will be using the waste of one industry, so we will be helping that industry in the disposal of their waste. Instead of disposing of, we are using that waste in treating the waste of another industry. And this particular work is already published in a very, very good journal, elsewhere journal, that is Clean Soil and Clean Air Water, that is there. So these are the conclusions which I would like to, I have already shared with you. Now the optimum dose, like I told you in Fenton process, the what plays important is the optimum dose of iron and H2O2. So in for this particular textile waste, which contains RB4 and RO16, the Fe2 plus and H2O2 dose was 1:7, which helped in the removal of 90 to 97% decolorization and almost 62% reduction in COD. So This was about my first one. Now, the second case study, I'm not going to go into the detail of the second study. I hope I'm not crossing my time. Just I'll take 5 to 10 minutes more. Now, see, there I had taken the dyes. The second one is the wastewater. This is industrial wastewater. Actually, the wastewater was taken from the industry.
No issue regarding the time.
Okay, ma'am. Thank you so much, ma'am. Thank you so much. Now, when industry people approached us, they said they wanted their wastewater to be treated using the Fenton process. I said, okay, let me try. So we have a group of teachers, those who work on this. Now, this particular paper, this work is also published. So with me, Sarika Vithalkar ma'am, Seema Shivaso ma'am, and this is Sathe sir. He is a person belonging to the industry. So he is also associated with this. So the work that we have done in this is already published in Material Today's Proceedings. So in this, what is done now, there we were talking about RB4 and RO16. That means they are the reactive dyes. Now here we are going to talk about nitroaromatic compounds, which are normally used in chemical industry for the production of dyes, explosive, pesticides, and pharmaceuticals. Okay, now these nitroaromatics are also very, very harmful, very, very harmful for environmental. Okay, why? Because they normally contain nitrophenols and nitrobenzene, and nitrophenols, if they are present in the wastewater, they are highly toxic. That is why, and these nitrophenols, you know what? They have strong electron withdrawing groups. And because of these electron withdrawing groups, they are poorly biodegradable by aerobic treatments. So that is why we need to go in for first, before applying the biological process, first the chemical process is like I had shown you in that particular flow chart when we were talking about biological processes. So first chemical process is done. Now based on the chemical process, the results of the chemical process, then biological process is done. So because this wastewater, it cannot be subjected directly to biological treatment process. That is why it was then subjected to Fenton process. So again here, this industrial wastewater was collected from Hindustan Organic Chemicals, that is the industry present in Rasayani, Navi Mumbai. Okay, now here also in this particular process, we had followed the same process of optimizing contact time, optimizing iron dose and H2O2 dose. Okay, now here I would like to bring to your notice that in this particular, we had to raise the iron dose because nitroaromatics are more poorly degradable, or they need more strong oxidant, more doses of oxidant as compared to reactive dyes. Okay, so here the time required thankfully was same, because here also when we varied the time from 30 to 120 minutes, we took the time to 150 minutes also, but here at 150 minutes there was no changes, so we optimized the time to 120 minutes, and the maximum COD removal was 39.22 and the maximum color removal was 23.3 percentage as when it was done at 2 hours. And when you can see, if you see here, time at 30 minutes only, there was almost 25%, then 35%, then 36. So after 60 minutes, almost 35 to 40% reduction in COD was there. But now the question arises, when we were getting almost comparable 35 to 40% COD reduction, then why did we go up to 2 hours? Now, if you see the color removal, The maximum at around 60 minutes, the color removal was only 12%. And it increased to almost 23% at when the reaction was performed at 120 minutes. That is why the reaction had to be continued till 2 hours, and fortunately till that time almost 40% reduction in COD was obtained. Now similarly, if you see iron dose in the previous one, if you see, I had done it only for 500, 200, 300, 400, 500. But here, the reaction was we had to increase it till 600 ppm. Here I have converted into millimolar, but if I talk it up if I convert it into ppm, it is 100, 200, 300, 400, 500, and 600. At 600 ppm, in 2 hours, we got 37.4% removal and 62.4. But here you can see at 8.95, that is your 500 ppm only, we got maximum color removal of 50% and 71% of COD reduction. These are the figures again. You can see as we increased the dose, so iron dose also plays an important role. We increased the dose of iron and there was reduction in it. Now, if we talk about H2O2, H2O2 again, here we had to take higher concentration of H2O2, and here the critical value, if you see here through graph, if we see it in graph, the critical value is around 0.7 for here. So in this particular one, the ratio of this iron to H2O2 was 8:21. But Fenton method can be used for treating the nitroaromatic compounds. Now, case study 3, we were gradually increasing the complexity of the wastewater. Okay, this is recalcitrant. That means very difficult to treat. Okay, here it was a combination of all the industries. Here the industries, the water was taken from, hello, hello.
Ma'am, you can continue. You're audible. Ma'am? I think there is a network issue from ma'am's side. Can wait for a minute. There's a network issue, I think. We can wait for a minute or two. Ma'am will be joining us shortly. Ma'am will be joining us shortly. Participants are requested to wait patiently. For the time being, participants are allowed to put their queries in the chat box. Ma'am has joined us.
I'm so sorry. I'm so sorry, all the participants. I don't know what happened all of a sudden.
It's okay, ma'am. You can continue.
Okay. Is it visible and am I audible?
Yes, ma'am.
Okay. So, like I was telling you that we were increasing the complexity of wastewater. So now this was the most complex one, wherein there was a combination of wastewater from various different industries, and it was, the color was so strong. It was very, very dark brown color, and the characteristics were fluctuating. So this was really, it was a challenge for us. It was a challenge for us to treat this water. But let me tell you, my dear friends, that here also, in this process also, Fenton could treat this particular wastewater. That was, if you concentrate here, I have written it, combined effluent treatment plant of heterogeneous industrial sector. So heterogeneous industrial sector, that means from various industries, from pharmaceutical industry, from textile industry, from different industry, this was done. And this particular wastewater was subjected to both photochemical treatment, photocatalysis was done, and Fenton was done. And if you see here, with photocatalysis, only 10 to 5% reduction was there, whereas but with Fenton process, it was 80 and 72%. Color, when it was photocatalysis, only there was reduction in color by 10%, and COD reduction was only 5%. But when this was subjected to Fenton process, then color reduction was 80% and the COD reduction was 72% after 2 hours. So in that way, I can say that Fenton process is one of the most important advanced oxidation process that can be used for treating varied wastewater that are received from different types of industries. Okay, now in the last, I would just like to tell you that nowadays, looking into the environment, government is asking the industries that are producing very, very toxic chemical wastewater, they should go in for this technology, that is zero liquid discharge, that is ZLD, meaning no discharge, zero discharge of wastewater from industry. Whatever water they are using in the industry, whatever water they are using, they have to recycle it or they have to recover it and reuse it there itself. They do not need us. They have to plan their process in such a way that is recycle, recovery, and reuse of the treated wastewater. And thereby, they will not discharge in situ. They will do everything in situ. They are not, जो भी निकल रहा है उसी को वो कहीं ना कहीं यूज करेंगे. एंड नॉर्मली ZLD में जो कंपोनेंट्स है फॉर ट्रीटमेंट, वी यूज reverse osmosis, evaporator, or crystallizer normally. Okay, and why, what is zero discharge, why is it required, and how it is done? We all know it very well. What it is, I have already told you. Why it is required, because of the availability of fresh water for process, difficulty to comply with the regulatory bodies, and regional considerations. So because of this, zero discharge means that all reactant materials are converted into products and all the processing aids are reused and no waste is produced. Actually, this is the ideal process, but normally real process hota hai. Yeah, ideal hai, but in real process, fraction of raw material is lost as a waste or consumed or degraded processing is including water and become a part of the waste stream. So normally real process hota hai, ideal process hona मुश्किल है. And how to approach a zero discharge, ये आप देखेंगे diagram में, तो it will be very very clear कि design of zero discharge facility क्या क्या involve करता है. So with this, I would like to say uses of treated wastewater. Please, treated wastewater is not a waste but a resource, and it can be used in so many ways: land application, groundwater recharge, saline water, lake supplementary, recreational uses, direct and indirect use for potable purposes. But only thing is that the reuse method should be applied only after high degree treatment, only after high degree treatment to avoid the danger of contaminating. That means tertiary quaternary treatment process also needs to be applied. Matlab polishing should be done and then can they be applied for reuse methods. Thank you so much for your patient hearing, and I need your valuable feedback and suggestions wherein I can improve upon, and or you can suggest, madam, you can apply this method also. This is my number and this is my email ID. Thank you so much for your patient hearing.
Thank you so much, ma'am, for this wonderful explanation. Now the panel is open for discussion. Participants can raise their hands or directly ask the question.
I think there are no questions, ma'am.
Okay, ma'am. Thank you so much again, ma'am. Ma'am has explained and focused on industrial wastewater treatment, as industrial waste is having a huge impact in our ecosystem, starting from the physical, chemical, and biological characteristic of water to the selection of appropriate treatment technology. Dr. Rao has made us a very technical, given us a very technical and logical spectrum for better best analysis. Ma'am has also explained the Fenton's process, which has incorporated for nitroaromatic compounds, which are widely used in chemical industries. Also, ma'am has introduced us to the zero liquid discharge, which means zero discharge of wastewater. Also, ma'am has explained very logically what, why, and how zero discharge could get incorporated. Lastly, ma'am has explained various uses of wastewater, treated wastewater. So thank you so much, ma'am, for this wonderful presentation.
I would once again like to thank Hardas ma'am, HOD Physics Department, and her entire team. Suvarna Saude ma'am, convener, Satish Tiwari sir, co-convener, and the entire Physics Department for organizing this wonderful STP and giving me an opportunity to be a part of it. I once again thank you, ma'am.
Thank you, madam. Thank you, madam, for such a nice presentation, which was very informative and so interesting topic it was.
Thank you so much, ma'am. Thank you, ma'am.
Thank you for joining us.
Thank you, ma'am. And I'm once again sorry for this technical glitch. I don't know why all of a sudden there was internet failure here in the office. So I'm once again sorry for that.
No problem. No issue.
Thank you, madam. Thank you so much for the wonderful presentation.
Thank you so much, Suvarna ma'am. Thank you so much.
Thank you so much, ma'am. Thank you, participants. Participants are requested to join us exactly at 2:20 p.m. for the next session. Thank you.